Okay. So let's remember where we are. So in the last class, we started talking about subsequence regrets. So the idea is to play in an online linear optimization setting, like learning from expert advice kind of setting that multiplicative weights and family play in. But with a more refined goal than just having no regret as measured on average over the whole subsequence, which is the kind of thing that multiplicative weights gives us. Instead, we thought, maybe what we're going to have is a collection of subsequences that we care about. Those subsequences could depend on the history in arbitrary ways. They could depend on features we have available at classification time. And they could even depend on the action that we ourselves play. And we want to have no regret simultaneously on all of these subsequences. Okay, so just sort of like motivating examples of each sort of these. One was sort of adaptive regret. We want no regret, not just overall, but on every contiguous subsequence of time, so that at any moment, no matter when we start paying attention to the algorithm and no matter when we stop paying attention to the algorithm, we're guaranteed to have no regret on that subsequence of time. Okay, that's called adaptive regret, and it corresponds to like capital T squared subsequences just defined by the pair of endpoints when you start paying attention and when you end. We might want something that's sometimes called groupwise regret, that maybe we're making predictions, say, about people. Maybe we think that there are certain properties that we can read off of their medical chart, things like demographics or medical history, like people who are female, people who have a history of high blood pressure, that may or may not be relevant to the decision task at hand. And so what we'd like is that not just overall, but on this, for each of these demographic groups, on the subsequence of rounds for which we were making predictions about people from that group, that we should have no regret, that we should do as well as whatever turned out to be the best choice in hindsight. Okay, so this would sort of be something like, we're doing A/B tests or clinical trials, say, to figure out what is the best treatment. And we'd like to have guarantees that we do as well as the best treatment overall simultaneously for these different subsets of people that might intersect. That would be an example of subsequence regret, in which the subsequences are defined by external context, which is allowed. And then finally, our last example was something like a swap regret. We want no regret on the subsequence of rounds for which we played action 1, and no regret on the subsequence of rounds for which we played action 2, because, for example, this would give us good game theoretic guarantees like convergence to correlated equilibrium. Okay, so those were sort of general motivations for studying this thing called subsequence regret. And the way we formalize that is with subsequent selection functions. So we're given a collection of subsequent selection functions. Each one takes as input, say, the time step, or if you like, the transcript of what's happened so far, allowing the event to depend on anything that has happened thus far. Takes as input the action played by the learner at this round, so it allows the event to depend on the action, so we can encode things like swap regret. And it takes as input external context, so we can get things like groupwise regret. And it outputs a number between 0 and 1. In the language that I've been using, where I sort of talk about no regret on particular subsequences, that would be realized if the output was either 0 or 1. There we'd think of the output as being sort of the binary indicator for whether today is included in some particular subsequence or not. But in fact, like, nothing we're doing mathematically is going to require that. You can think of it as outputting like a number between 0 and 1, which you can think of something like a real valued weighting, telling you the degree to which you care about this round in some particular subsequence. And if we're given a collection of subsequent selection functions and we somehow play in this online linear optimization game against an adversary where every day we choose an action. Well, first we observe the context, right? So we have all of the information available to determine as a function of what we do, which subsequences we will contribute to. But otherwise, we're playing in sort of the standard online linear optimization game where we choose an action, the adversary chooses a cost vector. We say we have no subsequence regret or subsequence regret alpha if simultaneously for each of the subsequence functions in our collection and simultaneously for each action in our action set that we are hoping not to have regret to, that when we look at the sum over all of the rounds where we weight each round by the subsequent selection function. So maybe we even zero out the round if that round is not a member of the subsequence and not otherwise. We look at the sort of per round, like the instantaneous regret we have in that round, which is just the difference between the cost for the action we chose and the cost for action I. Okay, so this is only a generalization of external regret, the kind of regret we've been studying. External regret just corresponds to subsequence regret, where there's one subsequent selection function and it selects every single day. It's the constant, the constant one function. Okay, so we could ask for something like this, which is a stronger guarantee. Okay, now last class, what did we do? We showed how you can embed this problem in this sort of online multi-objective optimization framework. And we sort of bounded the adversary moves for first value of that embedding, of the game defined by that embedding. And we saw it with 0. The subsequent selection functions sort of like don't matter, because if the adversary moves first and tells you the cost vector, you just go second and play the action corresponding to minimal cost. And you will just have, if you do that, 0 per round regret, because you're doing the optimal thing round by round. And so in particular, you'll have no regret, even as weighted by any of these subsequent selection functions. And so the general theorem we proved about online multi-objective optimization meant that indeed it was possible to give algorithms that have diminishing subsequence regret for any collection of subsequence indicator functions. And we actually got really good bounds. We got the same bounds that we got from multiplicative weights, okay, that sort of promise regret just on a single subsequence, but simultaneously for all of the subsequences. And what we paid for that was only an extra logarithmic term, logarithmic in the number of subsequences. So information theoretically, at least, you can ask for like a ton of subsequences and it doesn't hurt you very much. Okay, so like asking for something like adaptive regret, which is only sort of adding an additional additive like log t term, which we were sort of paying anyway. Those things are basically for free. At least information theoretically, at least in terms of the bounds. Now, how about the algorithm? Well, the generic algorithm that comes out of the AMF framework, like if it's a polynomial time algorithm, if it's a polynomial action game, but it's not like the friendliest algorithm. It's not the thing you'd immediately want to implement, because at every step of the algorithm, you need to solve like a non-trivial optimization problem. In particular, like how does this AMF, this generic like AMF optimization algorithm work? Well, at every round, it defines a zero-sum game, right? What's the zero-sum game? Well, it's the game whose objective function comes from weighting the D sort of objectives you have in the multi-objective optimization problem by weights that you got from running a copy of exponential weights. Now you have an objective function for like a one-dimensional zero-sum game, and the algorithm would have you compute a minimax equilibrium strategy for that game. Okay, you could do that. I mean, there's only k actions. You can do this in time polynomial in k, like we even have seen how to do it in this class. But it's like a non-trivial computation. So it would be nice, that, right? So if the story ended there, that would mean that information theoretically going from external regret to subsequence regret cost very little. This sort of logarithmic term in the regret bounds in terms of the number of subsequences, but that computationally, potentially it costs you a lot, right? Like you went from just running multiplicative weights, which just has this explicit formula for what the weights are. In fact, a simple, constant time update you can do every round, to having an algorithm that requires that you solve something like a linear program at every round to compute this min-max equilibrium. Okay, so we'd like to, we don't want to pay that big computational cost if it's not necessary. And so what we'd like to do is to get algorithms that are more efficient than that, or really just better implementations of the same algorithm. That's just sort of what we're going to do this class. We're gonna give and analyze algorithms for variants of this problem that don't require solving, like an arbitrary linear program, that will either hopefully have a nice closed form distribution when we can do that, and maybe more generally need to do something, but hopefully something that is sort of simpler, like some kind of standard matrix computation rather than sort of solving an arbitrary optimization problem. Yeah.
But when you said like that essentially says like
yeah.
So I guess the ground optimization and that part constraint can just become, you just put them all into a linear equation. Yeah, I guess.
What are the weights?
Okay, but you could choose a way. I mean, it's the same with bridge regression, right? Don't say, oh, the coefficient needs to be below X. You say, okay, let's penalize high coefficients enough that a weight.
So I think what you're getting at is sort of the difference between distributional optimization, like optimization when you've got a distribution, and regret bounds against an adversary. So if you think about something like, okay, so when you put, it's true that in general, if you have a constrained optimization problem, at least if things are nice and convex and strong duality holds, you can generally take constraints and put them into the objective and solve this Lagrangian optimization problem. By the way, what is the Lagrangian optimization problem? It's a min-max problem. If you were originally minimizing in the, if you're originally minimizing an objective subject to some constraints, the Lagrangian is solving a zero-sum game. It's minimizing over the primal variables and maximizing over the Lagrangian variables. These are sort of the variables in the dual linear program. And you're solving a min-max game against an adversary where you choose the primal variables and the adversary chooses the dual variables. Okay, so Lagrangian optimization, by the way, also solving a zero-sum game. Now, if the problem is fixed, which it is if there's a fixed distribution, then the optimal dual variables, they're just something. Like there's you don't know what they are until you solve the min-max problem, but like in principle, there's just like some optimal dual variables. And so like if there was only one constraint, there's only one dual variable, and its value is something, and you could just optimize the primal subject to the Lagrangian where you've plugged in the optimal dual variable and get the solution. Now, okay, so that's something like what regularization is doing in a regression problem. So like ridge regression or lasso, this is sort of bringing into the Lagrangian the constraint of an L1 or an L2 norm sort of constraint. And so if you just sort of, okay, if it's only one dual variable, you can, in sort of a one-dimensional search, plot out all of its values and pick the one that corresponds to learning something of a norm you're happy with, and there you go. Okay. Okay, so maybe like 2 obstructions to trying that approach here. By the way, there are similarities to what we're doing since we are solving a zero-sum game at every round, and you can think about what the adversary is doing as choosing dual variables. But two obstructions to just sort of making this happen straightforwardly in a way that doesn't look a lot like what we're doing now would be that, number one, there's no distribution. So there's no fixed set of values that are like the optimal dual variables throughout the run of the algorithm, right? Like depending where you are in the subsequence, if I look at the optimization problem that corresponds to satisfying a bunch of constraints on the prefix, depending which prefix you look at, it's like going to be a different empirical distribution and therefore correspond potentially to very different values of the dual variables. Second, since there's potentially a lot of constraints, you need to figure out what those dual variables are. Like exhaustive search is just not going to work anymore. So those are sort of the reasons why you need to like do something here. Make sense? Good question. But yeah, maybe it's worth, I mean, what we're doing is not that different in the sense that the reason why you can bring constraints into an objective in the Lagrangian is because the Lagrangian problem is no longer a minimization problem, it's a min-max problem. Okay, so just like a helpful way to think about Lagrangian duality, if you like zero-sum games, is that, say I want to satisfy a bunch of constraints. Suppose, let's define the game where I get to pick the primal variables. And then the adversary gets to pick a violated constraint. And the cost is the degree to which the constraint is violated, like the difference between the left-hand side and the right-hand side, given the variables that I chose. Okay? So the value of this game, if the optimization problem is feasible, the value of the game is 0, because if there's a feasible solution, then no matter what, think about the adversary going first. No matter what constraint or convex combination of constraints the adversary chooses, you can just pick a feasible solution and not violate any of them. Similarly, if I play something that's not feasible, the adversary is going to pick a violated constraint and punish me. And so in this game, the min-max optimal solutions are the feasible solutions to the original constraint optimization. And so in some sense, what's going on here is like kind of similar, right? Like what's going on in the adversary moves first algorithm we analyzed. We've got multiplicative weights playing over the constraints, right? Like multiplicative weights is kind of like trying to choose put its weight on subsequences for which the regret is maximized, essentially. And then we're sort of defining a zero-sum game by weighting the increments in each of these subsequences by multiplicative weights. So you can think about multiplicative weights as, in that reduction, sort of optimizing for the adversaries like Lagrangian variables. And we're sort of solving this optimization problem online in this min-max sense. Yeah, okay, good question. Other questions? Okay, where was I? Algorithms. All right, so last class we wrote down an algorithm, but we didn't analyze it. It was not an algorithm for the fully general case. It was an algorithm for what we called action-independent subsequences. Okay, what is an action-independent subsequence? It's just a subsequence defined by a selection function that happens not to look at the action argument. Okay, so it's like, I know after I see the context, the relevant thing is after I see the context X, I know for sure whether today is a member of each of the subsequences or not. It does not depend on what I do. Okay, so there's no self-reference here because what I need to do is choose an action. So first I know what subsequences are active, then I act. That's going to make things simpler for us compared to if my action itself feeds back into what subsequences are active. Okay, and in this case, we claimed that there was actually a very simple algorithm to solve this problem. And by simple, I mean there's like even there's no optimization problem to solve at all. There's just like a closed form solution for what the algorithm should do at every round, the distribution on actions it should apply. And it was this. Okay, and it had a simple interpretation. Like even though there's this is like some long expression, lots of symbols. This is made up of objects you are familiar with, right? Like this is a simple distribution. Let's just remember what it is. So like, what's this expression here? Inside here, this is proportional to the weight that exponential weights would put on expert I if we were only running this copy of exponential weights on the subsequence of rounds that were active for one of the particular subsequent selection functions, right? Because what is this thing? It's just the exponential of the regret to action I on the subsequence of rounds for which subsequent selection function E, includes that round. Okay, so this is just like, if we were running a copy of multiplicative weights only on those days for which this subsequence E was active, this thing here is the weight that it would put on action I. Right? Just playing things exponentially proportional to the regret to that action. Now, like, by the way, why don't we just do that, run have a copy of multiplicative weights run for each subsequence, and like when subsequence 5, when we have a day that belongs to subsequence 5, run that copy of multiplicative weights for one round. Well, we could do that if the subsequences didn't intersect, right? If something that was a member of subsequence 5 wasn't a member of subsequence 6 or 7. But we can't do that because they do, right? Like it might be that the copy of multiplicative weights we're running on subsequence 5 suggests we play a different distribution than the one we're running on subsequence 6. And what do we do if, today is a member of subsequence 5 and subsequence 6? Well, here's what this algorithm does. It looks at which of the subsequences are active today, which is something that makes sense because these are action-independent subsequences. And then it just adds together the multiplicative weights distributions for those subsequences that are active today. And if you add up a bunch of distributions, you don't have a distribution anymore, so we normalize so that everything sums to 1 again. And we just play that distribution. That's what this algorithm does. And more generally, since these subsequent selection functions don't have to be binary, it takes the weighted sum of all of these copies of multiplicative weights weighted by the degree to which the corresponding subsequence is active today, and then normalizes. Okay, so that's the algorithm. Make sense? And then the theorem we stated last time but did not prove is that the E regret, the subsequence regret on this collection of subsequences E we give it, was bounded by something small. For root T log M plus log K. Okay, where M is the number of subsequences. Okay. And this wasn't some number we just made up. This was the bound we proved on our generic adversary moves first multi-objective optimization algorithm when we instantiated it with exponential weights. Right, like this is just the bound we proved like a couple of classes ago for this generic multi-objective optimization algorithm when we feed in M times K loss functions, which is what happens in the reduction from subsequence regret to multi-objective optimization. Yeah.
Sorry, go back to for that probability. Is it like
I guess only to the extent that you can think of exponential weights as kind of being like a softmax, right? Like exponential weights is, in some sense, just the softmax distribution on the regret that we have to each action so far. And this is the sum of those distributions weighted by the indicator functions for which subsequences are active. Okay, and not like you're right, like how did we derive exponential weights? We did use this softmax potential function, so you're right that like pulling the thread on this, you do eventually get to softmax, but I don't know if that's the most direct way to think about it at this point. Okay, good. Okay. So the theorem is actually saying a little bit more than this. It's not a coincidence that this is the regret bound. The claim is that actually this is the generic algorithm for multi-objective optimization that we analyzed, instantiated in this particular multi-objective game. Okay, so the claim is that like that algorithm, remember, just comes up with a weighting for these loss functions. The weighting is according to an exponential weights distribution, and then says at every round, play the minimax equilibrium. The claim is this is not a different algorithm. What we have written here is just a closed form expression for the minimax equilibrium of that game. Okay, so it's not a different algorithm, it's just a different implementation of the same algorithm. It turns out that you don't have to solve a linear program. In this case, the minimax equilibrium strategy has a closed form, and it is this. Okay, so that's what we want to prove. If we can prove that this is an equilibrium of the multi-objective optimization game that we need to solve at every round using the generic algorithm, that will be done because this is the regret bound we proved for the generic algorithm. Okay, so sort of the name of the game in the proof here, like we're not going to be directly proving a regret bound. We've already proven the regret bound. We're going to be proving that this is a minimax solution to the game defined in our generic multi-objective optimization algorithm. Make sense? Okay. So let's try to do that. Okay, so let's remember what is the game that we need to show that this is the minimax solution for. Okay, so it's the game for which, okay, the learner is the minimization player, their strategy space is distribution over actions, the adversary is the maximization player, their strategy space is cost vectors. And what was the utility function? Well, it was this. The learner plays distribution P, and the adversary plays cost vector C. It was the sum over all of, in this case, subsequent selection functions E and actions K. Okay, why is it the sum over these? Remember, in the generic game, it is the sum over all of the loss increment functions. These are going to be weighted by the multiplicative weights distribution. And in the encoding of the subsequence regret game as a multi-objective optimization problem, remember there's one loss increment for every subsequent selection function E and action I. Okay, so we're summing up over the loss increments here. Okay, well, summed up over the loss increments, what we're doing is we are weighting with the exponential weights distribution today's loss increment. Well, what's the exponential weights distribution on, what weight does exponential weights put on event E and action I? Well, it's the exponential weights distribution. So it's e to the 8/2 times the sum from 1 to t minus 1 of the regret thus far on subsequence E times the regret thus far on subsequence E to action I. Okay, that's what's in the numerator. In the denominator, is the normalizing term, which just sums up over all of the events, E prime and actions J prime of the same thing, except here we're looking at the regret on subsequence E prime. To action J. Okay, this is the exponential weights weight. What is it weighting? It is weighting today's loss increments for subsequence E and action I. Okay, so the thing this is multiplying is today's loss increment, which is just the weight that subsequence E has today, times the the instantaneous regret that we will have today if we play action P, the adversary plays action C, to action I. Okay. So this was the utility function. It is the weighted sum over all of the loss increments in the subsequence regret game, weighted by the exponential weights distribution. Okay. So what do we need to show? Well, we know, because we already proved it last class, that this game has value 0. Right? Like we sort of, it's easy to figure out the value of the game in this case if you just imagine what happens if the adversary goes first. If the adversary tells us the cost vector, we put all of our weight on the smallest coordinate, and the value of the game is 0. Okay, but now we don't want to just know the value of the game. We want to have a minimax strategy. What is a minimax strategy? Well, it's a distribution P such that when I evaluate this big expression, no matter what cost vector C is plugged in, this will always evaluate to something less than or equal to 0. Okay, so the thing that we need to show is that when we plug in for P, this big expression, when we plug in this big expression for P in this other big expression, that no matter what C we plug in, the thing we get back is going to be less than or equal to 0. Okay, that is like the thing we need to show. That is the property that a minimax strategy, that is what defines a minimax strategy in this game, because we know the value is 0. Okay, does that make sense? Like most of the rest of this is kind of going to be algebra, but I just want to make sure that the logic is clear, like the thing we need to show. This is the objective function for the game. The value of the game is 0. The claim is that this is a closed form expression for the minimax equilibrium strategy. The thing we need to show is that when we plug that big expression in here, that no matter what C gets plugged in, this always evaluates to something less than or equal to 0. Yeah. Yeah, good. So okay. Reason one, we proved it last class, but reason two, we can. It was simple enough that we can reprove it right now. Consider the adversary moving first, and you best respond. Okay, so you know C. Here's what I propose you do. You play the distribution P that puts all of its weight on the coordinate of C that is smallest. Okay, let's say that's coordinate I star. So then this inner product, this is just Ci star. Okay, so Ci star minus Ci, well, Ci star is only smaller than Ci. So this term is non-positive. And this is a probability, so it's non-negative. And so non-positive times non-negative, we get a non-positive number. So if the adversary moves first, it's very clear what to play, the action that has smallest cost, according to the adversary's cost vector, to best respond, and that causes this to evaluate to 0. And so there must be, and because it's a game. Oh, you're asking, like, how do I know the value of the game is not negative? Oh, because the adversary can also, if they want, guarantee cost 0. They just, if they pick the cost vector to be all zeros, then nothing the learner can do can get a negative value. Yeah, so good. So strictly speaking, last time we proved that the value of the game is less than or equal to 0 with this argument, but the value of the game is also greater than or equal to 0 because the adversary could just pick a 0 cost vector. So the value of the game is exactly 0. Good. Make sense? Okay. Okay, so like conceptually, it should be clear what to do. Like you might have lots of angst about the fact that we need to plug in one giant expression into like another giant expression, but like that is only syntactic angst, not semantic angst. Okay. Let's see. So I actually want to use the fact that both of these expressions are long and complicated in like a pretty similar way, actually. Right? So like this is long and complicated, this is long and complicated, but they're both long and complicated because they're both kind of similar, right? Like, look at the numerator here. It's kind of the same as the numerator here, except here we've got like this extra factor of E. And similarly for the denominator. Okay. And so I sort of want to say, okay, like in the numerator here, it looks a whole lot like the numerator here, except over here we've got this extra factor of E, but here's an E. We've got an E floating around over here. So why don't we let the numerator borrow that E? Okay. And maybe I can write this big expression in terms of this thing, in terms of this big expression. Okay, indeed I can. Just sort of by algebraic manipulation, I can rewrite the utility function as EIT times the inner product of T and C minus CI. Actually, the sum over I of this, just we've dealt with the numerators so far. So we've got, yeah, like basically, I moved this E over here, and then we have the same numerator. And we need to deal with the denominators too, but for now, let me not do out the algebra and just sort of give a name to what the denominator is. call it phi t. Okay, there is some such denominator.
Not really. Like dividing one by the other.
You want me to write out the denominator? I can do it.
Are you thinking?
I'm saying there is a definition for phi of t that will make that. Let me do it. Okay. All right. Let's.
I'm satisfied.
Okay. There is a number that I can write here. It is in the notes. It has summations in it. That makes this true. Okay. I guess what's relevant about this number is that it does not depend on P or C. It only depends on sort of history. Okay, so the utility does, the denominator doesn't. The utility depends on based on what's in the numerator. Okay. 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 Let me go through this, and if you think I pulled a fast one here, I can write out the denominator, and we can do the. Okay. All right. Okay. Good. So, let's start manipulating. So just expanding out this inner product. This is the sum from 1 to k of PIT times the sum from j equals 1 to k. This is sort of the index over the inner product of pj times cj. Okay, I've just written out the inner product as a sum minus ci. Okay, and we still have this normalization term. Okay. And just expanding out again to separate these two terms into two sums. We've got the sum from I equals 1 to k and from j equals 1 to k of PIT PJ CJ minus the sum from I equals 1 to k and j equals 1 to k of PIT CI. Or in other words, the sum from I equals 1 to k and j equals 1 to k of CJ times PIT PJ minus PJT. where here I have sneakily renamed the index of summation. We've swapped the role of I and j, but that's okay. Those are just names. Okay. So this is the utility as a function of P and C. Okay. Now the question is, what happens when the P that I plug in is PT? Let's remember the question we're after. If I plug in PT to this utility function, do I force the value to be less than 0? Okay, so far I haven't done that. Like the PT has shown up only as pattern matching. Like this thing looked like PT. So I used that similarity to write it in terms of PT, but this expression is still written out in terms of some abstract P. There's a distinction here between P, the argument to the utility function, and PT, this particular distribution. And so the question now is, now that I've written things like this, can I see easily what happens when I plug in P equals PT? Okay, well, what happens when I do that? Well, what I see is that the utility, when I plug in PT, and the adversary plugs in C for some value C, well, it's 1 over this normalization term. Times the sum of from I from 1 to k, and the sum from j ranging from 1 to k of Cj. Okay, now P and PT are now the same thing. So Cj times PIT times PJT minus PJT. Okay. And no matter what Cj is, this quantity must be less than 0. How come? Well, when I look at this inner term here, on the right-hand side, I'm subtracting off PJT. What am I subtracting it off from? Well, another copy of PJT multiplied by a probability. Probability is less than or equal to 1, so the thing on the left is smaller than the thing on the right. Didn't matter what the costs were, because the constants multiplying each of these non-negative costs were each 0 or negative. Okay, so no matter what C you plug in, the cost is 0, or the utility is at most 0, which means that PT is a minimax strategy for this game because the value of this game is 0, and that's what a minimax strategy means. Which means that this algorithm here, which is just playing according to this distribution, is actually at every round playing the minimax strategy of this game, which is the algorithm we analyzed 2 classes ago and proved this regret bound for. Okay, so this is just an implementation of that generic algorithm that we already analyzed. It happens that when the subsequence selection functions are action independent, the minimax equilibrium strategy actually just has a closed form. Yeah. The M, what is? Like, you mean like, oh, so what is the theorem we proved for this generic algorithm? It's that if you have a d-dimensional optimization problem, then your regret bound will be like 4 root t log m. And what is m in this game? We have 1 objective for each subsequence cross action. So there's m times k of those. Log of m times k is log m plus log. Natalie.
General framework for this, right? It's sort of ignoring the self-referential and they get very tough done. What like how much is this? This is like every algorithm that's in the conference's goal.
What do you mean every algorithm that can accomplish this goal?
Typical framework for achieving particular guarantees.
Like, what is this goal, first of all?
Is, I guess it would be something like I am looking for managed threat, like context, and you say like, okay, well, if I want to like think about like what like the entire space of algorithms that can guarantee that, like here's a
Okay, so are we talking about multi-objective optimization problems?
yeah. EMF framework.
Okay, so you're asking something like, can every algorithm that guarantees, diminishing AMF regret be viewed as playing a minimax equilibrium strategy of a game that somehow looks like a weighted, maybe weighted by some no regret algorithm, a weighted combination of the increments. Okay, so just noting up front some sort of obvious variance. You could use a different no regret algorithm to weight things, then the weights would look different, and the form of this would look different. Like you could get a variant of this that sort of looked more like gradient descent weights by using gradient descent. So I guess also, like, just as in regular regret, in general, for AMF regret, for a small number of rounds, you could just do like totally arbitrary things and it wouldn't hurt the algorithm that much. So it's not that every algorithm must be doing this at every round. So maybe there's a variant of your question that's like, is it approximately doing this like most rounds?
The energy distant from some algorithm.
Yeah, it's a good question. I don't know any. I don't know how to. I'm not sure I even know how to formulate that as a precise question, and I don't know any. I certainly don't know how to prove in any sense that the answer to that question is yes. But I also don't know that the answer to that question, however it's ultimately formulated, is no. It would be really cool if somehow, yeah, it would be cool if there was some sense in which there was like a canonical algorithm that without loss of generality you could analyze. I don't know the answer.
The minimax solution.
Not necessarily. Minimax solutions are not necessarily unique. I don't know about in this game. Oh, but I mean, you could have potentially totally different algorithms for solving the same class of multi-objective optimization problems that like are not playing equilibrium strategies of this game. Okay, so like there is a sense in which every no regret learning algorithm that has a guarantee against an adversary must be playing an equilibrium strategy against an adversary in the larger game, sort of defined in algorithm space, where you get to pick any algorithm, the adversary gets to pick any algorithm, right? Because bounds against an adversary can just be defined as the outcome of this larger game in algorithm space. And so if you're getting close to the value of the game, you must be playing in this larger game an equilibrium strategy. So in that sense, the answer is sort of like yes, like trivially, like any algorithm that has guarantees against an adversary, optimal guarantees against an adversary, must be playing something close to a minimax equilibrium strategy in this very large game where the strategy space of the learner is sort of all algorithms. Here we're doing something much more specific, which is that we are avoiding even thinking about this much larger space of, much larger game, because it's hard to think about solving a game, where the strategy space is all algorithms. And so we're solving sort of at every round a locally defined game, defined just in terms of the action space that round. And that's what I don't know is sort of without loss of generality or not. But yeah, formulating and answering that question would be in either direction, I think would be super interesting. Good. Other questions that live up to that one and interestingness? Okay. How about now we just sort of, before we move on to what we might do if our subsequences depended on the action, and get an algorithm for things like swap regret. Why don't we just to tie up threads here, be a little bit more precise about these kinds of motivating subsequence bounds we've been talking about that happen to be action independent. So adaptive regret and group clustering. Okay, because we now have an algorithm that can efficiently solve those problems. Let's just be precise about what those problems are. Yes, that is exactly what I propose to do now. I've spoken it out loud before, but we've never written it down, so let's do it. Let's write it down. Okay. Okay, so informally, again, what is adaptive regret and why does multiplicative weights or exponential weights or whatever not necessarily promise it? It is the desire that if I run my no regret learning algorithm, starting at round 1 and ending at round t, even if I sort of zone out and don't start paying attention to it until round t1, and then I manage to maintain my attention until round t2, and then I zone out again, that even on this subsequence of rounds, I should be doing as well as the best action in hindsight. Why does multiplicative weights not satisfy that? Well, you know, what's multiplicative weights doing? It's sort of weighting each expert exponentially in proportion to the gain that we've seen from that expert so far. Okay, so to use like a nice example that Natalie's always telling me, suppose there's 2 actions, and for the first t/2 rounds, action 1 has gain 1, so action 1 is really good. Action 2 has gain 0. Okay, but then at round t/2 it switches, and action 2 starts having gain 1, and action 1 has gain 0. Okay, so yeah, action 1 is like super good, action 2 sucks up until like halfway through, at which point action 2 starts being good and action 1 starts sucking throughout. Okay, so the cumulative gain of action 1 will become t/2 at round t/2, and it'll stay t/2 throughout. The cumulative gain of action 2 will be 0 all the way up through round t/2, at which point it'll start slowly climbing up, finally tying the cumulative gain of action 1 at t/2 at the very end. Okay, so what's the algorithm going to do? Well, it's going to have this distribution that's weighting each of the 2 actions exponentially in proportion to their reward, cumulative reward so far. So very quickly, it's going to start playing action 1 almost all the time. Okay, when we get halfway through to round t/2, action one will have this sort of like insurmountable lead, literally insurmountable, because, you know, it'll have cumulative reward 2/2, which action two will only manage to just tie at the end of time. Okay. And so it's going to keep playing action one throughout. It's going to keep playing action one until close to the very last round. On the very last round, it'll be uniformly randomly playing between action one and two, because only then will the two actions have equal cumulative reward. Up until like the last few rounds, basically the algorithm will just be playing action one. Now this is no regret overall, because if it plays action one every time, it gets payoff 2/2. That's what the best fixed action did as well. But it means if I start paying attention only at round t/2, then the algorithm will appear to have terrible regret. It'll have good regret overall because it sort of built up this sort of excess gain in the first half, and it's sort of like spending that down in the second half. But if I just look at the second half, the regret bound is bad. Okay, so adaptive regret is designed to like fix this problem. Like it's not allowed to do that. It needs to be that no matter what interval I look at, even if I started running the algorithm beforehand, it should have a good regret bound on that interval. Okay, intuition makes sense? Both why this is something you might want and why something like multiplicative weights won't satisfy it? Okay. So adaptive regret. So given action space A, which say is just k actions and a transcript, the expected regret to action I on the subsequence ranging from t prime to t for some t prime less than t, both between 0 and capital T, is just, well, the regret on the subsequence. It's just the sum, not over all time, but just over time starting from when you started paying attention at t prime all the way up to t, of the difference between the expected regret of the algorithm, the expected reward, the expected cost of the algorithm, and the cost of consistently playing action I. Okay, and if we say that we have adaptive regret alpha, what we mean is that the maximum over all of our actions I, and also over all subsequences between t prime and t of the regret on that subsequence to action I is at most alpha. Okay, so Natalie. Yeah, so again, Yes, so like, what are we going to show in a moment? What are we going to sort of remind ourselves in a moment? We're going to say we can get adaptive regret root t. Now, what's the rewards if they're between 0 and 1? What's the maximum value that the cost of the algorithm could be on a subsequence of length L? It's at most L. So a bound of root t will not be especially interesting if we're looking at an interval of length smaller than root t. It'll be non-trivial for intervals of length root t. Now, it is, as I mentioned last time, but we're not going to show in class, but we can talk about offline. It is possible by instantiating this sort of AMF framework with fancier no-regret algorithms than exponential weights to get fancier subsequence regret bounds out the other side that don't depend on root t, but root the length of the subsequence. So for adaptive regret, it is possible to simultaneously bound the regret simultaneously on every subsequence by sort of square root the length of that subsequence. You'll maybe pick up like a log t term somewhere by doing this. And so this will sort of be non-trivial for, instead of only being non-trivial for subsequences of length smaller than root capital T, it'll be non-trivial for all subsequences of length smaller than something like log t, just so that the constant and log terms don't overwhelm the bound.
That's very cool.
Yeah, good. Yeah. Sorry, but again, the subsequences intersect, right? So like, what do you mean copy? Like these are like a particular round is a member of a lot of subsequences. So one thing what you have in mind, like suppose I said, okay, what I care about are subsequences of length 1,000, and I'm gonna like partition my time up into like disjoint blocks of 1,000, rounds 1 to 1,000, 1,001 to 2,000, 2001 to 3,000, and so on. And I'm just going to run multiplicative weights over each of those blocks. And like when I get to a new block, I'll restart a new copy of multiplicative weights. Well, it's true that your regret on each of those blocks will be, only root 1,000, but your regret overall will add up over those blocks. Right, so your overall regret won't be root t. It'll scale linearly with the number of blocks. Okay, so that would not satisfy a subsequence regret bound of root t, because you also have to measure your, right, like this is over all subsequences, including the whole thing. Right, so yeah, like it is, like we're gonna, like this algorithm will do it, but this algorithm has a way of dealing with subsequences that intersect. Yeah.
Is this way more heavy on
yeah, maybe something like that. I mean, like what's going to happen, so just to maybe like write one more piece of notation so that I can more easily point to this algorithm here. This is just subsequence regret. For the collection of subsequences that I'll call E adapt, which consist of the subsequence indicator functions that I'll call E T prime T for all T prime and T between 0 and 1, where the subsequence indicator function, or I'm going to want to plug in T in a moment. Let me call this S prime and S, where the subsequence indicator function E S prime S, when I plug as input around T is just the indicator function that T falls between S prime and S, somewhere in this interval. Okay. There's T squared of these. And so, yeah, so M is T squared. And so what is the adaptive regret bound we're going to get out of here? Well, it's going to be like 4 root T log T plus log K. So compared to like multiplicative weights regret bound, we have made, like what we have is an additive term of log T that we didn't have before. But that's kind of low order. Like we've already got a root T. Yeah, so the cost of adaptive regret on all T, of sort of having low regret on all T squared of these intervals is root T, or sorry, is log T. Yeah, like this is some particular like case of intersecting subsequences, right? So like, yeah, like if you only wanted regret on subsequences of length 1,000, you could just run multiplicative weights independently on these blocks, but then you'd have like good regret bounds on a small scale, but you'd have bad regret bounds on a large scale. And this is somehow giving you good regret bounds on all scales simultaneously. Okay, with the caveat that they're not so good for short sequences because the bound we proved here still depends on root capital T. But my claim is that by using slightly fancier versions of this algorithm, you can get this bound actually to be sort of root T minus T prime, like root the length of the subsequence. You'll still pay for the log T factor. Okay, does that make sense? Okay, and somehow like what it's doing that multiplicative weights is not doing is that it is, for every time, when it's deciding what to play at every time step, it is summing up the regret bounds or summing up the weights of the copies of multiplicative weights that could have been run simultaneously on any subsequence or on any interval of time that today's time step is a member of. So all intervals whose left endpoint is in the past and whose right endpoint is in the future. Okay, makes sense. Okay. Okay, so this is, just encoding subsequence regret, encoding adaptive regret as subsequence regret. We can, plug it into this algorithm solves it. Maybe just to hammer in the last nail, we talked informally about groupwise regret. What's that? Okay. Groupwise regret. Now we're going to use the context space. Fix a context space X and a collection of groups G, which is just a collection of subsets of X. So this is a set of groups. A single group is just an arbitrary subset of the feature space. Okay, so maybe like the context space is the set of all medical records that your doctor could potentially bring up on his iPad when you walk into the office. And groups could be like the set of all medical records that are indicative of a family history of diabetes, or the set of all medical records that are indicative of female sex assigned at birth, or anything else. Like any way you could divide up the population by what's in their medical record, that could be a group. Okay, they can intersect. This is a set of groups, so I want it to be written in a calligraphic font, which is easy in LaTeX, but hard when I'm writing on the board. So let me just like kind of like write some squiggles to make this a little fancier. What did you say? I have to cut. Yeah, I'm gonna have to. I might have to like do it again is a problem, but see what we'll see what happens. Okay. So the regret on group G, which is one of these groups, the regret on group G, the action I is just the regret, except I'm not summing up over all time. I'm only summing up over those time steps for which the context was a member of group G. Okay, so only those time steps for which the patient had diabetes, only those time steps for which the patient was female. And, you know, I'm summing up the usual regret term, the difference between the cost of the algorithm and the cost of action I. And we say that we've got like groupwise regret bounded by alpha if, when I look at the maximum over all of the actions and also over all of the groups, let's do this one more time, in our collection of groups of the regret on that group to that action uniformly, those are all bounded by alpha as well. Okay. And again, just to sort of note, groupwise regret is subsequence regret. This is just subsequence regret. On the collection of events, e.g., where there's one event for each group in our collection of groups. And the subsequence indicator function for a particular group now is a function only of the context and is just the indicator that the context at that round is an element of the relevant group. Okay, so like summing up over all of the rounds for which the context was a member of that group, that's the same thing as summing up over all of the rounds of the regret on that round times the indicator that the context was a member of the group. We'll be just zeroing out the rounds that for which it's not. Okay, so that means that if we want to have no groupwise regret, so we make a single set of decisions, but we can say ex post that for men and women, our decisions are nearly optimal. For white people and black people, our decisions are nearly optimal. For young people and old people, our decisions are nearly optimal. We can do that, even though the same person might have a gender and a race and an age. These are not mutually exclusive. These are intersecting groups. Okay, they're intersectional groups. Again, there might be many groups that we care about. This manifests itself as asking for subsequence regret on a collection of subsequences whose cardinality is equal to the number of groups that we care about. And so we can use this algorithm to get a regret bound that scales only logarithmically with the number of those groups. So, okay, computationally, the running time of this algorithm is linear in the number of groups, because what are we basically doing? We're sort of separately running a no regret algorithm on each group. But because the same person can be a member of multiple groups, we're aggregating those by, whenever a new patient arrives, say, adding up the distributional predictions of each of those algorithms for the groups that they happen to be a member of, and then normalizing. Okay, so our running time, because we have to add up, we have to sum basically in this step over all of the groups that a person is a member of. Our running time is linear in the number of groups, or at least linear in the number of groups a single person can be a member of. What we're really summing up over here is the number of groups that today's patient is a member of. So the running time is actually, at each round, linear in the number of groups that today's patient is a member of. But our regret bounds are only logarithmic in that. So sort of asking for these intersectional regret guarantees, information theoretically at least, very cheap. Yeah.
The number of constraints, the number
The number of possible subsets. Yes, the number of, like, yeah, the number of possible subsets of the feature space, that's really big. That's exponential in the feature space. And so we wouldn't get reasonable bounds. So what's a reasonable feature space, by the way? Like, suppose each medical, just abstracting things, each medical record can be described by d binary bits. So the feature space is of size 2 to the d already, and the number of subsets of the feature space is of size 2 to the 2 to the d. So it's sort of hopeless to try to ask for no regret on every possible group. And again, when thinking about what is possible and what is not, I think it's helpful to think about the game of trying to guess the outcome of a fair coin. You shouldn't be able to do that. Of course, if I'm defining groups based on like atmospheric conditions where I'm measuring, 1,000 different things to 10 bits of precision, probably my measurements are going to be distinct every single day of the coin flipping. And I could say, well, I'm just asking for subsequence regret on a rich enough collection of subsequences that, like groupwise regret on a rich enough collection of groups that happens to, have every day is a member of a unique group, then I'd be able to like predict the outcome of a coin flip. So like basically the number of groups, if I don't care about running time, I just care about non-trivial regret bounds, I can potentially ask for no regret on an almost exponential number of groups. But in most feature spaces, like in the dimension of the feature space, the number of possible groups is going to be doubly exponential. So you can't ask for no regret simultaneously on every possible group, but realistically, any group that you think might be decision relevant, because exponentially many is a lot. It also can't be, well, what did you say? Well, it doesn't depend on t at all. These indicator functions depend only on context. Sure. Yeah. Can't be it is when m becomes exponential in t that this bound becomes trivial. Questions? Okay. So next class, we'll think about what happens if the subsequences depend on the actions.